Last time I presented to you the concept of search space, equivalent subsolutions, and states, and also some tips about them. Now it's time to put those concepts and tips in practice. The first problem that we are going to tackle is named Zig-Zag. You can see a link to that problem on the description below. A sequence of numbers like this one over here, it's called Zig-Zag. If when plotted, it goes up and down in every step like this. Or more precisely, if the difference between successive numbers strictly alternates between positive and negative. For example, this is a zigzag sequence, but this is not. The problem is, given a sequence, for example, something like this, find the longest zigzag subsequence. A subsequence is a sequence that can be obtained by erasing or deleting some of the elements of the original sequence. For example, this is the original sequence, and if we delete these two numbers, so these three, what is remaining here is a subsequence. And also every sequence is a subsequence of itself. For this case, if we delete this number that I just wrote out, the remaining number is a zigzag subsequence. And for this case, this is the longest one. To get most from this video, I encourage you to try to solve this problem by yourself. And if you are not able to do it, then watch the solution and ask yourself what was lacking in your line of thought and how you could change it to do it better next time. For solving this problem, first we have to ask ourselves how to reframe this problem as finding an optimal sequence of choices. And I think the most natural way to do it is to first check the first number of the sequence, and then we decide if included on the subsequence or not. Then check the second number of the sequence and decided if included on the sequence or not. Then go for the third and decide if included on the sequence or not, and so on. So we can summarize the choices as for each number s sub I in the sequence, we can decide wherever if we include it in the subsequence or exclude it. But we cannot just include all the numbers. There is also a restriction that we need to fulfill. And that restriction is that at all times our subsequence must be a zigzag sequence. Now with this in mind, note that this restriction is not descriptive enough. If we already have many numbers in our subsequence, how do we know if adding the next number would break the subsequence or not? Then for describing the restriction in way more precise, we can do it by checking again the definition of what is a zigzag sequence. After checking the definition again, it should be clear that if the sequence ended increasing, the next number should be smaller than the last one. And if the subsequence ended decreasing, then the next number should be greater than the last one. This can be rephrased in the following way. Even when it may seem like trivial how to rephrase the stuff, it's often very useful to rephrase it in some way that could be more formal or more precise. Because when we rephrase it in ways like this one, then it's easier to work with them. And when we reformulate things to get another conclusion. Let's go back to the example that I showed you before. If we already have our subsequence like this, then if we are going to add 15, for example, to the subsequence, or we are thinking if we want to add it, then let's get the value of d that is here. D equals 5 in this case. Then d is greater than 0. So the next number in the subsequence should be less than 10. So it cannot be 15, it cannot be 10, but it can be 5. Then if we have 5 already on the subsequent, in this case d would be equal to minus 5. So d would be less than 0. So in this case, the next number should be greater than 5. So it could be 16 or it could be 8. But notice that it cannot be 10 nor 15 because the number should be later in the sequence, not just having a greater value. Then what we do need to know if we can add a number to the subsequence or not. For that, we would need to know which one was the last number of the subsequence, and also we need to know if the previous number to the last one was greater or smaller than the last number, or it would be the same if we are expecting the new number to be greater or smaller than the last. So in order to know if we can add a new number or not to the sequence, we need to know when the index of the last number inserted, and if we are looking for a number greater or smaller than the last one. And this information can be used for representing a state. So the states can be represented as a ordered pair of index, and if the next number should be bigger or not. Also notice that this index can have n possible values, and this variable next is bigger can have two different values, true or false. So the amount of possible states would be only n times 2. This is completely feasible. Let's draw the state transition in order to deduce from there the recurrence. From this state, from a state where the last element has this index and there is this flag indicating if it's expecting the next element to be bigger or smaller than the last one, then there are these two options. One is to don't add any number and just finish the subsequence like that. Then this is basically the base case of the recursion. And the other option would be to add the element with index plus k as the index. And if it was expecting bigger, then it would be expecting the smaller, and if it was expecting the smaller, in this other state that is moving to, it would be expecting bigger. And this sign over here, it's basically a negation sign. And also k needs to fulfill these conditions as well. So the state can move to a k that fulfills these conditions, and it could move to several possible values of k. And now with all this diagram in mind, it should be much more easy to find the recurrence now, or the optimal substructure. Now with the state transitions in mind, we should be able to find the recurrence relatively quickly. Please note here what this recurrence really means. This would be the maximum amount of growth that the subsequence can have if the last element has the index I and the value of the flag that indicates if it's expecting a bigger or a smaller next element. So because of that, if we don't add anything else to the subsequence, it's possible to get a 0. That this would be the base case of the recursion. And if we add another number to the subsequence, it would be a number with index k that is greater than I, and the flag would have the opposite value, and then it's this +1 that indicates that we are adding an extra number to the count. And this is an abbreviated way of expressing the restriction of Zig-Zag. Finally, this is an implementation of the solution that I have just explained. If you have any questions, don't hesitate to leave it on the comment below. And this is all for now. I hope this video was useful to you, and keep practicing, because next time we are going to do something more challenging.